Two. Yeah, I guess we can just start now. Uh, this is a new subject for me as well, and it's the topic is design environmental benign process. What it mean by that is that it's actually not a technical class, so lucky for you, you don't have to remember or memorize a lot of things, but it's about understanding the design principle to make a green and sustainable process. And the framework that we're going to be looking at throughout the class is green chemistry. So there are 12 principles of green chemistry. And my part, I will cover from principle 1 to 7, and then Professor Shalida will take over from there. The course objective, I will go rather quickly. So you should be able to explain the role of chemical engineers to, in enabling and preventing environmental impact, interpret and apply 12 principles of green engineering, critically evaluate the chemical process using the different metrics. So we will learn different metrics like E factors, PMI, energy efficiencies, and so on. And then propose some solution. And then also we will be looking at the real world case study. And lastly, communicate sustainability driven engineering decision effectively. So that's the purpose, the objective of this course. And there are some reading materials already on course syllabus, so feel free to go have a look. The grading, so out of 100%, the quiz and exit ticket will be 15%. Assignment will be another 15%. Midterm is 35 and final is 35. So my part, as I mentioned, I will cover the introduction for today. And next class, actually today we will cover 2 classes. So introduction and then the overview of the 12 principles. Next class we will not have a class, so it's a holiday for you, but we will have the assignment to be submitted. And then I will talk about principle 1 and principle 2 together, 3 and 4, 5 and 6, 7, and then at the end we'll wrap it up by guiding you through different evaluation metrics to determine whether the process that we talk about is actually environmentally benign or not. Right. So in my part, I will have 3 assignments, and in some of the class we will have some also like a quiz or exit ticket at the end. And this is Professor Shalida's part. So as you can see here, we'll also talk about principle 10, 11, 12, and some software where I think she will have somebody from outside to come and teach us as well. And then some case studies, and then the final presentation and project reflections. So that's the second part after the midterm. Okay, any questions so far regarding the evaluation? So there is no attendance, but I like to keep it there so then I know who actually comes and who didn't come. So yeah, if you haven't done, yeah, just okay. So today will be a rather relaxing class because it's just an introduction, and hopefully at the end of the class, I want to give you like a brief overview of the principles that we will apply in our design thinking. So let's start from the beginning. As a chemical engineers, we good at converting, long chain hydrocarbon to different kind of products. And so far, the industry before 1970, the industry was driven heavily by the end product. We want A plus B equals C, and we want C so much that we don't really care about what come after it or before it. And the wake-up call was during 1969 when a river in the US caught fire. The whole river caught fire. And so this river, before it caught fire, it is known to be black and smudgy and very bad, smelly. And one day it caught fires, and the whole world kind of woke up from the old way of doing engineering. So you see a lot of organizations being formed after that 1969 fires. So, for example, in the US, they lead the way, right? Because it's a country where the incident happened. So the EPA, you must have heard, Environmental Protection Agencies, or EPA, was created after that, right? We have also the Clean Water Act, also created after that, 1972, right? Established industrial wastewater regulation and wastewater treatment standards. What is safe, what is not safe was mentioned in this Clean Water Act. That's in terms of regulation, but in terms of public, right? We after that fire, very big fire, we people also wake up and think about the environment more, and that's led to the first ever Earth Day. Anybody ever heard of Earth Day? We don't have that in Thailand, but when I was in Japan, we had a Earth Day where it's all about green stuff and people come and discuss about the environmental issues. And that was the first time that this Earth Day being held in 1970. And yeah, there also some policies like NEPA being developed back then. This was the poster of the first ever Earth Day, right? So the quote there was, if you are not part of the solution, you are part of the pollution, right? So that held true to today. If you are not the solution, you are the part of the pollution. As a chemical engineer, we want to be the solution. We don't want to be the pollution. The battle to restore a proper relationship between man and his environment has begun. Right? That was kind of a wake-up call and the main slogan of this Earth Day. Right. So, you know, before before that day, the way we do engineering was we think about end of pipe, meaning that we create what we want, right? We always want to make something we want, but whatever come after that as a byproduct, we treat it afterwards. But because of this, we started to think more on the process itself, not just the treatment. Okay, so let's talk about historical engineering mindset, right? So as I mentioned, back then we often just focus on maximizing the yield, right? To get what we want as much as we can, minimize the cost, make sense. And as I mentioned, treat waste after generation. And why the mindset no longer works, right? Because we have limited resources. We, as you know, we dig what petroleum, crude oil from underground. It is a finite resources. You take it, you burn it, you create a lot of environmental impact, right? That's the science part, but the world is also looking at you as a chemical engineer. People look at SCG chemicals, how they make products, right? There are many regulations. So regulation also put the pressure on the chemical engineers and any kind of engineer in general to make the process more clean. And of course, the public is also looking, right? So that's why the mindset that we used to have, we have to transform it to change it into the green engineering mindset. And they are, as I mentioned, it's not a a rule where what you have to do one, two, three, but it's more like a framework for your thinking and for your when you design the product or process. Okay, so what happened before 1980? So this is how we used to look at the process. We have A plus B equals C and many ways to come, right? I forgot, maybe you should put A plus B equals C plus D, and D is the waste, or the byproducts, right? This then harmful chemicals, then now being treated into the less harmful chemicals and released to the environment. And I call this thinking the end of pipe solution, meaning that we treat it after the fact, after it being created, right? But now we have shifted from that, right? We try to shift from treatment to prevention. So the keyword in this slide is the shift between treatment and prevention. So green chemistry and engineering evolved directly from the idea and practices of pollution prevention and waste minimization. So that's the key concept that this class will talk about. So we'll talk about the way we think, the way how we shift from the treatment itself to preventing from it being created in the first place, and also if it is to be created, how can we minimize the waste? So let's talk about sustainability hierarchy. So we usually want to operate at the top, right? So this is the pyramid of the sustainability approaches. So you have here from the top prevention, reuse, recycle, treatment, and disposal, right? It makes sense that disposal is the least sustainable approach we can take, where prevention is the most sustainable, and this also correspond to the cost and the risk as well. So as you can see here, if we prevent it from being created from the first place, the cost is lower than, dealing with, the disposal and the waste after the fact, right? And also the risk increases as we go down the ladder. So yeah, have this image in mind. Okay, I will not talk about this again, but yeah, I think I already mentioned everything. So this course existed because we want to chemical engineer want to design, the process that is benign and have the least impact to the environment. Okay. And in terms of let's look at the 12 principle of green engineering. But before that, I have to start with the 12 principle of green chemistry. So this was created first, right? So you have the system A plus B equals C. In terms of reactions, in terms of chemists, we also think about waste prevention. And these are the 12 principles of green chemistry, such as waste prevention, avoid creating waste, atom economy. I think this is similar to like mass balance, where we want to optimize in the atomic level, the end product to be as high as possible and less waste. Right. The third one is less hazardous synthesis. We want to use and generate safer chemicals. Fourth is design for safer chemicals, meaning make product effective but less toxic. Safer solvent. Yeah, when you think about chemical synthesis, and if let's say if you want to make product C, and the product C has in terms of thermodynamics. It doesn't want to be formed. So in that case, you put a lot of reactant and you add a lot of solvent to help driving the reaction toward the product C you want. Uh, is that sustainable? Even though you get more product C, but maybe the waste in terms of like the solvent is more severe, right? We also think about design for energy efficiencies. Run the process at ambient temperature and pressure when possible. 7 is use of renewable feedstocks. Prefer renewable raw materials. The 8 is reduce derivatives. Avoid necessary protection modification steps. Catalysis to make the process faster and and better. 10 is design for degradation. Ensure that the product break down after use. So the product shouldn't be lasting forever. Real-time pollution prevention, more like monitoring system for the process, for example, safer chemistry for accident prevention, reduce accidental risk. So these are the 12 principles that was created by Anastas back in 1998. And of course, when we look about chemistry, let's look at this first. When we look about chemistry, it's just a small picture compared to chemical engineers, right? So chemistry, we look at the process, the reaction, chemical reaction mainly, right? We look at, the safety of this reaction, the atomic economy, the yield, the waste. But in terms of chemical engineer, we think more on the sustainability of the product, the efficiency, the cradle to grave from the whole life cycle of it. Is it sustainable or not, right? So this chart gives a very good idea about what's the difference between green chemistry principle and green engineering principle. So I will stop here and give you 5 minutes to read this slide and each principle carefully, and then we will go from there. So yeah, please spend some minutes to read. ไม่เด็กเชฟเป้ไม่ค่อยดมยาดมเลยอะไรนะอ๋อยังไม่ถึงเวลา Do you see the difference? So for engineering principle, you will see that a lot of the principle mention about system rather than the reaction, right? So think systematic thinking, like talk about the separation, talk about the system that is safe by nature, for example. Right. So there are many overlaps, but yeah, the thing that we will focus is 12 principle of green engineering, but many because it was written by the same person. Um, First author is same. There are many overlaps, but they also differ and distinct from each other. Okay, so I would like to normally for the 12 principle, I would like to group it into three clusters, right? One is prevention and inherent safety. ขาประจำ Okay, so we talk about 12 principle, and I would like to cluster it into three, and we will go through each clusters. So the first one, prevention and inherent safety. What does it mean? So as I mentioned, we want to avoid creating hazard and waste in the first place. So this includes principle 1, 2, 3, right? Let me give you a brief introduction of one, right? Inherent rather than circumstantial. So there are two keywords, right? One is inherent and another one is circumstantial. So we want to design the system that is safe by nature. What I mean by that is that sometimes um, you can make this if you design the process, right? Sometimes the process can be controlled to make it safe. Like you have a monitoring system, you have fire alarm, you have a chemical safety control. That is circumstantial, meaning that the process itself is not really safe, but you have the safety measure to make it safe. That is the difference between inherent and circumstantial. So inherent mean by nature of the process, it is safe. For example, to produce polyethylene, maybe you can choose the dangerous way, or you can choose a really green and safe way, and there is no risk being existed in the process itself. So that's inherent. Okay, so that's the first one. The second one is prevention instead of treatment. So as I mentioned before, so this is what we learned from the past, that treatment is like solving the problem when it already exists, which is not really sustainable. So we want to create a process to prevent such waste. So the second one, the first one talk about safety, the second one talk about waste. So we want to prevent the waste from being created from the first place. So that's the second one. The third one is very important in chemical engineers because most of the process, let's say process A and B, A has a very high yield, but that high yield product or high selectivity product, you have a lot of solvent coming with the process. So you have to spend a lot more energy to remove those solvents to get the final product. Versus the second process, maybe you have less yield and less selectivity, but you don't need to separate. There's no separation needed. So these are the, for example of two distinct process that as a chemical engineer, we have to design the process that minimize separation, because often separation, for example, if you do the if you make ethanol if you make bioethanol from sugar, the process of distillation probably take up more than 80% of the whole energy required for the whole process to make 99.5% ethanol, right? So separation is energy intensive process. So we want to minimize it as much as possible. So that's the first clusters, the three principles. The second cluster discuss about efficiency and integration, right? We want to minimize resource use and avoid unnecessary complexity. So this include principle number 4, maximize efficiencies. This one we will talk about, mass efficiencies or atom economies, the reaction itself, what kind of input and output we get, how many of it is waste, how many of it is our final product, what is the efficiency. So here in the next class we will learn, in the next class we will learn about the waste metrics like what do you call E factor, and also the mass efficiency metrics. So here we will learn those. Number 5 is a really important concept as well. If I have to briefly explain, we have to design a process that respond to the real needs, right? Think of BYD, for example. BYD, they make cars because they can. They don't actually, right now there's not much demand for electric car in China, right? But they already built the factories to produce 100,000 car a year. So this is an example of the input push. So you can, and then you keep making as much product as possible. What happened? You have to dump the price in order to sell your car, which is already made and sit there doing nothing, right? Or for example, right now there are many Chinese products coming to Thailand because the way the factory there works is they want to run the factory at the maximum capacity all the time. So it creates a lot of product that now, because of because of the trade war between Trump and China and so on, there are many products that has to flush the Asian market, and Thailand is one of the victims countries where a lot of Temu product, a lot of product coming onto Shopee and Lazada and actually basically kills the Thai producer and Thai businesses, right? So these are the example of input push process. In the future, what we want to do is we want to design a process that respond to the market demand, right? So we don't create unnecessary waste or product. And if you create more product than you actually need, what happened? You have to spend money storing those, make sure that those are not being, going expired and so on. So there are a lot of costs associated with the input push process. So here in the next class we will talk about this and discuss how we can design the process to respond to the market. Conserve complexity is the next part of this cluster. This concept is it sounds complicated, but it's actually not that complicated, right? So complexity mean each each feedstocks, for example, in a chemical process. Let's say you have 99% ethanol coming in. It doesn't come to be used to produce like polyethylene, for example. You start from 99% ethanol. 99% ethanol comes with preserve value in it. It doesn't come free, right? 99.9% ethanol takes up a lot. To get there, you use a lot of energy for the distillation and so on. So if your process only need 14% ethanol to process, right? Diluting those 99.9% ethanol is a waste. And this kind of thing can be avoided, right? Or let's say you have a really hot steam coming in at 500 degrees Celsius. You want to use in the process that only require 100 degrees Celsius. If you just use that steam to run the 100 degrees Celsius, it's such a waste because that 500 degrees Celsius steam is very expensive, right? So these are the things that we have to consider when designing the process, where we have to think about the cost associated with the production of those feedstock that we actually use. Yeah, here they said avoid unnecessary mixing. So this is also another great example. Um, if your process produce two products, right, and it can be separated at the point where it's being created, that's the best. But if you are not designing for that, the two products come out in the same stream, meaning that you have to spend a lot of money separating them later. So yeah, that's the conserve complexity concept. Okay, so far, any questions? EV, do you have the slide? Yes. Okay. Good. Okay, cluster three. Cluster three mostly will be discussed by Professor Shalida, but we'll give a brief overview here. It's about system and life cycle thinking, responsibility. So it's about the end of life thinking, right? If I think I'm pretty sure most of you learn LCA and the right? Have you learned LCA? Yeah. So this deal with those things, and Professor Shalida will discuss about those. But in term of my class, I'm talk about principle 7, durability, not immortality. This is also very important concept. You know how we make chemical product that last forever without it actually being needed to be lasting that long, right? For example, this is about matching the requirements, the user's requirement with the lifetime of the product. I give you a very clear example. For example, PET bottle, right? What is the requirement of PET bottle that you are having? It should be light. It should be safe to drink. It should have a good shelf life. For example, it should be able to stay steady on the shelf for 5 years, for example, right? And that's the requirement. But in reality, the PET bottle that you buy can last for almost forever, right? Thousands of years. So how can we decide a product that fit the lifetime actually fit the requirement of that use case? And for what? To minimize the waste, right? You have chemical like PFAS, forever chemicals that has a really strong carbon fluorine bond that doesn't like to degrade, and you make clothing out of it, like Gore-Tex clothing, right? Gore-Tex jacket that is a waterproof jacket. But after that, it is impossible to break that um, um, materials down, so it will last forever. So back then, engineers, we like to make very durable product without thinking so much about the needs, whether it's actually gonna be any consequences from that after its, lifetime end of life usage, right? So yeah, that's the concept 7. And number 8, talk about meet needs, minimize access. So yeah, not overcomplicate things, to put it in the simple words. Process number 9, minimize material diversity. This is also important concept for us to think about. For example, when you design an iPhone, or when you design a chair, for example, if a chair, if the chair that you are sitting on has the same material, the whole chair has the same material, without any metal, without anything, just same kind of plastic, meaning that the recycling would be much easier, right? But if your chair consists of many parts, like iPhone, many circuit boards, different kind of thing, the recycling would be much, much harder. So that's also the way we try to think to minimize the material diversity. Integrate material energy flow, that's self-explanatory. So we want to optimize the energy flow of the process, and integrate different process. Like as I mentioned, if you have a hot steam and you need only the low energy steam, maybe you integrate another process to do the heat recovery and so on. So that's the integrate material and energy flow. Number 11, design for commercial afterlife. So this is similar to the concept that I mentioned about material diversity. So it's about it's the aftermath of recycling. So if you design, like in nature, for example, if you design nature, basically let's say the material that nature design, for example, is cellulose of the tree, right? Cellulosic material of the seed of the trees, like tree trunk, right? So during the lifetime that the tree needs that material for, is just to grow, to be as high as possible, to get more sunlight, to transport water from the root to the top. So that's the lifetime, the first lifetime of that material. But what happened after that, right? That material become useful for other organisms, microorganisms like fungus, to eat and to fix nitrogen and put more nitrogen into the soil, so that more trees can be sprout out of the soil. So these are the kind of thinking that we want you to think, where you create some material and also think of that material, what happened after the end of the usage of that material. What happened to your batteries? What happened to your Tesla car batteries, right? Will it be recycled, or will it be used for different purpose? Like the battery in the car, for example, let's say battery in the phone, right? If the battery in the phone lose the 20% of the charges, let's say you use it for 2 or 3 years and it can only charge to 80%, right? You want to throw it away. You want to change the new one. The same thing happened for the car. If the car cannot be charged to 100%, let's say the capacity only reach up to 50%, you want to change the batteries because of the use case of the car. You need to have it. You need more energy to drive longer. But if you design it well, that batteries from your Tesla car that now has only 50% capacity can be used for household energy storage, right? Because in your house, you don't care so much about space and weight, right? If you talk about, single house, right, you have more space. So you can use that battery. It's like a second life of that battery can be used to be a buffer, to be a home energy storage solution to keep what to store your solar energy, for example. So these are the things that we have to think about, right? And the last principle is renewable rather than depleting. So this is really straightforward. So we want to change from non-renewable to renewable resources, right? Okay, why I call this class a framework, right? It's about thinking principle because there are too many design choices. You all familiar with the design class. There are many factors that you have to optimize. But here what we want to give you is the framework to think, right? It will act as a filter to narrow down your design choice, right? And it will help different metrics that you will learn will help you make a smart decision. Okay, back to this chart again. Spend 5 minutes to understand this chart and the difference between green chemistry and green engineering. I think you already understand it. So the differences, let me say it again. Green chemistry, we deal with the molecular level focus, reaction pathway, solvent, reagent, toxicity, while the green engineering, we deal with unit operations, integration, energy integration, materials, waste flow, separation, for example. So a green molecules can still be a green molecules can still be in a bad process, right? Even if we design, let's say green chemistry people, they design very good molecules, but if the process is bad, it still can be bad for the environment. So yeah, the two have to work hand in hand to create a sustainable process. Okay, I just want to show this chart rather quickly. So as you know, UN has created this framework called Sustainable Development Goal since 2015, and it will be used toward 2030, and it involves seven frameworks. And I just want to point out here where where chemical engineer fit into this sustainability efforts, right? So yeah, we play a very important role. What I want to mention here is we play a very important role in creating a sustainable world. So as a young engineers, I want you to know that your what you do matters, and 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 it will make an impact if you can make your process cleaner and solving different problems that the whole world is now trying to tackle. Okay, fast forward to chemical industry today, right? Um, we are responsible of a lot of greenhouse gas emissions. And not only that, we also responsible for a lot of energy consumption as well. So 6% of global greenhouse gas emission come from chemical industry. 7 to 8% of global final energy consumption come from chemical industry. Right? We use a lot of solvent, and this solvent create environmental impact. We also create a lot of wastewater in different industry like pharmaceutical, dye, making textiles, or even making fuels. One liter of biodiesel can in this lifetime maybe use like more than 1,000 liters of water. So that our industry, our chemical industry also fight for water resources and so on. So because of that, that's why we want to make it more clean, right? So mostly we are driven by four things. One is regulation, two is cost and risk reduction, three is competitiveness in the business, and fourth is long-term resilience. So let me give you an example of the major pressures in the in the industry that related to us. One is the high CO2 or greenhouse gas emission from ammonia process, ammonia production, methanol production, ethylene production, like and cement, right? We release a lot of toxic component into the atmosphere or environment, like aromatic solvents, volatile organic compounds or VOCs. PFAS is one of the main problem, like Teflon and many surfactant containing PFAS component. And this material, as I mentioned, is very stable than anything. So if it released in the atmosphere, it will be accumulated in the in the environment, in the food you eat, and it's known to have effect to us, to make us infertile, this kind of PFAS material. So it's very important we as a chemical engineer we replace these materials, heavy metal toxic. Another pressure that we should look at is plastic waste. We create more than 400 million tons per year of plastic waste, and only less than 10% are being recycled. So this design principle will help us to be able to recycle more. Let me give you an example of Cafe Amazon cups, right? I heard they serve more than 2 million cups per day, like the Cafe Amazon cups, plastic cups. And if you go to Cafe Amazon, you will see the bin, recycling bin they have, and they ask you to separate the cup and then throw it in the waste. But you know how many cups were being collected per year? Less than 200,000 cups per year, not per day. So they serve 2 million per day, and the whole year they only can collect 200,000. So you see, a lot is driven by the human behaviors. When we buy Cafe Amazon, we never finish it in the cafe. We have ice and so on, and we just bring it home and throw it in somewhere else. Never bring it back to separate. So that's create a lot of waste. So that's why this number exists. Less than 10% is being recycled. Not only the complexity of the product, but the human behavior also play a role. Okay, for those who had ever learned from me, I love this chart so much. Right, this chart is give a very brief, like I think concrete idea of where we want to be. Let's look at the left side first. Right, as a chemical engineers, what we used to do and what we still doing is we take the long chain hydrocarbon from the ground, we dig it up for free, a bit of digging cost, But that long chain hydrocarbon, we refine it and we create different starting materials, basic building blocks, like the Lego. And that Lego is being used to convert it into products and into different use cases, like plastic for different, application like vehicle, fuels, pharma, and so on. What we do, we optimize this energy flow process, and we try to reduce the environmental impact. And I think we have been doing very good in that. But as we are trying to move away from the finite energy source to the renewable energy, we have to transform ourselves a little bit. You will see here fossil fuels. If you learn mass balance, right, and if you want to burn it or pyrolysis or different gasification, for example, if you look at the mass balance, you will also always see that some carbon dioxide being created, right? So it's even if you try to optimize this process, make it as clean as possible, the reaction itself by nature create pollution. So there are right there are certain things we can do, and there are certain things that we already reach the limitation. So I argue that as a chemical engineer, the future of chemical engineer should move toward renewable fuels, right? This can be small molecules like syngas, carbon monoxide, hydrogen, um, renewable or bioethanol, like this. The replacement for fossil fuel can be some renewable energy, renewable fuels. And as a chemical engineer, we have to find a way to connect the dots, right? From that starting material, how can we get there to our final needs, final human needs, the goal, right? So basically our job is to design the new process, the new conversion chain that create less or minimize environmental impact. So I would like to call it as a chemical engineering of the post-fossil age. Okay, and from this picture, we will link it back and forth between our 12 principle that we will be talking about. So yeah, let's let's look at some case study that I would like to show you today to 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 help you think about the 12 principle more, right? The first one is about plastic bags. As we know, we create a lot of plastic bag for, plastic shopping bags. And you let me, as I mentioned, the lifetime of the plastic bag that we need, the usage of the plastic bags only is probably only 1 day or two, right? You carry it once and then you throw it away. And the shelf life probably can we only need it to last 2-3 months, for example, if you can manage the supply chain well. But the plastic bag that we use nowadays create is lasting forever, and it end up in ocean and so on. So many countries try to ban, including Thailand. We many shopping and many places they charge money now for plastic bags, right? And many countries already banned the single-use plastic bags and promoting the biodegradable or bio-based alternative, right, as a preferred option. The promise is that this kind of renewable or this kind of biodegradable plastic bag is made from renewable feedstocks like corn, sugarcane, starch, marketed as biodegradable or compostable, perceived as a solution to plastic pollution. That's the promise, right? So we assume if we use this kind of plastic bag, biodegradable bag, it is sustainable, but is it? So what literature actually shows is that biodegradable plastic bag, many of the plastic bag only degrade under specific condition, right? Typically industrial composting, high temperature composting facility, and many bio-based plastic are not biodegradable, and many biodegradable plastic are not bio-based. Another important thing is biodegradable plastics contaminate the conventional plastic recycling if not properly stored. This is also about human behavior, right? You have the separation bin for like PET bottle, but you see many people put plastic bag in it because they think, oh, it's the same. And if the biodegradable plastic bag is mixed with the non-biodegradable plastic bags, the whole separation and the whole recycling process become it become different story, right? So that's what the literature shows. If is there's the contamination law, like mix of waste, then it would be a problem. The feedstocks that I mentioned, corn, sugarcane, starch, to make that plastic bag also compete with food, land, water, and fertilizer uses, right? So it's a competition of resources as well. But those are the things we have to think. Okay, from this case study, what principle that is actually violate, right? So one thing that is quite clear is principle 11, design for commercial afterlife. The point here is if you okay, what Cafe Amazon is doing very well is they not only they introduce the biodegradable plastic cup for Cafe Amazon, but they also make the system to collect it, even though it's not really successful, but at least they try. But infrastructure, material that deploy without proper infrastructure for the afterlife or the end use is not sustainable. So that's principle 11, right? Principle 5, output pull rather than input push system, right? This is quite clear. The policy or the production is not driven by the actually the demand, but it's more driven by the policies. One day, Thai government just said 7-Eleven, you cannot give people a bag, you have to sell, or you have to change to renewable one. These are not driven by the real needs, but it's driven by the policies, right? Principle 6, conserve complexity. As I mentioned, what happened in reality is what happened? What I mentioned before, if the high purity waste, like plastic bottle like this, is mixed with low quality waste, make it difficult to recycle. So this are the complexity that is being lost, right? During the process. So that's also another problem that we see from this case study. Another one is I already mentioned durability rather than immortality. You see here that this material the requirement is only few months, but it lasts for forever. So that create a lot of waste, right? So I put here as a summary. So biodegradable plastic bags from this case study we see are conditionally beneficial, not inherently benign, right? Without aligned waste management system, they risk becoming a new sustainability problem rather than a solution. So I saw many of you compete in different, competition, creating different solution. I think this is one of the good example for you to think um, whether your solution is actually a solution or it will create another problem. So yeah, this 12 principle of engineering will help you to define, to identify those. Okay, another case study here, or another example is PFAS, forever chemicals. You see here, CF bond has a really large bond energy, 485 kilojoule per mole. Very, very stable, doesn't degrade easily. We use it to make waterproof jacket, right? What happened? It violated many, many principles, right? I will not go into the detail, but one thing is very clear is principle 7, too durable, and it's almost immortal, right? And PFAS, since it's a chemical bond, it's a molecules, right? Once it mixes into the water stream, it's impossible to separate. So at the end, eventually it will be ended up in the food, in the fish, in the animal, and at the end it will be end up in our body. So that's a principle for separation or removal. It's pretty difficult. So what happened? In order, what we can do to improve that, right? So this is a Gore-Tex company. So they've been relying on this uh, Teflon or PFAS material for a very long time. To be more sustainable, they changed the materials, right? This is this is they changed the material to give the same properties, but following many of the chemical engineering principles, right? Instead of using PFAS as a main component, they use expanded polyethylene, and polyethylene very well. It's the material we know very well, right? So using that create the same kind of material, but it doesn't last forever, and then create the waste issues, right? So they use principle 2 and 3. One is replacing hazardous and persistent material with safer alternative, switching from fluorinated membrane to hydrocarbon membrane. In terms of unit operation, eliminate fluorinated surfactant, simpler wastewater management, reducing toxic byproduct in polymerization, because making polyethylene is much easier than making the Teflon and the PTFE membrane, right? Simple environmental management and manufacturing site. Life cycle thinking, principle 6 and 12. The new material uses renewable electricity to produce for production of some for the production in some Gore-Tex facilities. Lower end of life risk. We already mentioned here that polyethylene is much easier to recycle compared to the Teflon or PFAS material. Supports long-term renewable rather than depleting resource use. So the polyethylene can be made from bioethanol and other small molecules. So eventually they will move away from fossil fuels and make the process more sustainable. Okay, these are the few last thing I want to communicate for this class, because I think we all tired. This is not really related to this class, but I want to mention here is because why sustainability matters, right? Why company want to achieve sustainability. It's not just about the fact that they love the world, they want to make a greener world, but by showing that we are sustainable, when you communicate to the employees, the company, the the employees become more, attached to the company, that, means we not only want to make product, but we want to make meaningful change to the world. So that's communication is very important, or communicating to the stakeholder and shareholders, right? People who are involved in our business. If we communicate that our company is sustainable, it 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 helps to bring more investment and to bring more trust to the company. And if you're interested in sustainability, you can read all these approaches in the sustainability report of most of the companies, right? You have Shell, even though Shell is a petroleum company, they do have sustainability aspect, and they do have put much effort to make their process more sustainable. Or even Patagonia, if you know, this is the advertisement from a few years ago. They said, don't buy this jacket. They know that the jacket is not sustainable. They know that people buy it because of fashion. So they said, don't buy it. If you already have one, don't buy it. Don't buy it because we make new products. Buy it because you actually need it. So these are the strong key message that the company can convey. So not only we do and we make better process, but we want to communicate, and it will eventually, and this is a key importance that I want to highlight, that doing sustainability doesn't equal less profit. You can see here from Apple revenue. So Apple report greenhouse emission every year. And you can see here that they reduce the greenhouse emission year by year. And what happened to the profit? It also grow up year by year. So it doesn't mean that we put a lot of energy, a lot of, doing things sustainably can become profitable if we do it right. And this 12 principle of green engineering will help you to achieve that. So that's the framework that we are trying to give here. So there is a group work, but I think it's okay. We don't need to do it. Okay, so what happened in the week two? So I'm going to Boston for a week to learn about entrepreneurship in deep tech in MIT, and so next week we will have a break, but instead of the class, I already teach the two classes today. So instead of the class, I will give you an assignment. And what I want you to do is go to the My Course View. There are two papers that I will upload. One is the 12 Principle of Green Chemistry. It's a very short paper, just like five pages or less than that each. Right? Go read the two of them, 12 Principle of Green Chemistry and 12 Principle of Green Engineering. Try to understand it. That's the first thing. The second thing is I want you to select a real process, right? So this is a part of the homework, right? Select a real process. For example, plastic bag production and disposal system, PFAS, PTFE, PFAS manufacturing, and wastewater treatment. This kind of thing, select one, something that you are interested in, or maybe it can be your previous competition or startup project, whatever. You can pick one process. Step two, I want you to describe the current process, right? Briefly describe the key unit operation, the reaction, what happened, the separation, the treatment, what are the inputs, material, energy, and what are the waste, emission, and byproducts. A simple block diagram would do. So pick the process, right? And then the step 3 and 4. Step 3, I want you to identify in that current process what kind of green engineering and green chemistry principle that it violate, or something that can be improved upon. Okay. So pick to each So you will read the principle first, you pick the process, you identify what is the current process unit operation, and then you identify what principle it violates. And lastly, you will propose a short redesign reflection. So it can be a simple thing, you can propose in this report about the change that is needed to make the process more sustainable or to make it even more profitable, for example. Okay, I think it's quite clear, and just submit the thing before the beginning of week 3. So the week 3 will be on 21st of January. So yeah, submit one night before and keep it short, 1 or 2 pages. Use ChatGPT, Notebook LM, that's fine. Just yeah, try to understand, and basically I want you to use ChatGPT and and AI to help you come up with the answer, but the important thing is I want you to understand. So to read it, to understand it, and to put it in your own word, to write it, in the format that you understand. What I hate to see in the report is different bullet points like ChatGPT usually generate, right? Don't put bullet points. Just put it in your own words, okay? All right. So this is an example of the thing I want to see, but yeah, as I mentioned, make it a sentence, not a bullet point like this. Okay. Any questions for this class? Otherwise, it's the first class. I don't want it to last too long. Kiwi, any questions? Sugar, any question? So many of you might ask, so I like to mention again, so this is not a technical classes where you have to learn many equations, right? It's about a principle, it's about a way of thinking, and many case studies that you learn and try to understand. Okay, so I hope that the first class today give you a good overview. Oh, we already finished. I hope the first class of this of this course give you a brief overview, a concrete overview of what we're gonna be learning, and I hope that by the end of this class, it will help you to it will give you the framework of thinking when you go into industry, to make the process or to improve the process and make it more sustainable. So that's what I want to deliver to you, and and a bit of thinking framework. Okay, so that's the main focus of this class. And if you study with me for the last solar class, you will know that my exams for this kind of class will be more focused on the understanding, the way of thinking. And I hate to see many people last time print a lot of papers. So it will be, I think you print more than 200 pages to the class. So that's not sustainable. So this midterm, we will do it open book. Okay, you can bring your iPad. Okay, to make it more sustainable. So yeah. All right. Thank you for coming today, and see you in 2 weeks.